You're welcome yet to another of our series of lectures. Today we want to discuss the chemistry of the halogens. The halogens. Halogens. As you do know, halogens are members of group 7 in the periodic table. They are the next group of elements next to the noble gases. In nature, halogens occur as diatomic molecular gas. They occur as F2, Cl2, Br2, I2. The nature of halogens descend. As you descend, the group decreases from gas to liquid to solid as you descend. I would wish to make an observation that in some periodic tables, you find out that hydrogen is kept above fluorine. Yes, to correct whatever erroneous impression you may have, the inclusion of hydrogen among the halogens is not because hydrogen is a halogen. No. Hydrogen is kept on top of fluorine because hydrogen needs one electron. It needs one electron to attain the electronic configuration of helium. It needs one electron. And all the halogens need one electron to attain the stable configuration of a noble gas. So for that reason, we will start by looking at the electronic configuration of the halogens. The electronic configuration of the halogens. So we start with fluorine. Fluorine bears the helium core. It bears the helium core and has 2s2 2p6. If you see the helium core, which is 1s2p5, 1s2, you realize that 2p5. So if you 5 not 6, please. 5 not 6. So if you see the helium core, you add 2 plus 2 plus 5 gives you the atomic number of fluorine. Just after fluorine, you have chlorine. Just after fluorine, you have chlorine. Chlorine atomic number 17. And the nearest core that chlorine can assume is the neon core, neon 10. And if you look at neon at 10, it has 10, you are left with 7, and that 7 will occupy 3s2 3p5. 3s2 3p5. Just under chlorine, you have bromine 35. Bromine 35. Bromine 35. Bromine will bear the argon core. Bromine will bear the argon core. Argon core. and argon 18, you are left with 17. 35, you are left with 17. And you ask yourself, how do we get 17 across? You see, you have 4s2, and because you have come down to the fourth period, you expect that the 3d will come in there, and you have the 4p5. That is the electronic configuration of bromine bearing the argon core. And as you go down, you go to iodine. Iodine 53. Iodine 53 will carry the krypton core. Krypton core. And when it carries the krypton core, you now ask, krypton 36. Krypton 36. 36. You realize that if you subtract 36 from 53, 36, you have 17. 7, moving there, 17. So you realize that you need to have 5s2, 4d10, 5p5. And that is the electronic configuration of iodine. And the last member of that group is astatine. Astatine, atomic number 85. 85. 85. 85. And it will carry the xenon core. Xenon core. Xenon core. And when it carries the xenon core, xenon is 54. Xenon is 54. So if you subtract 54 from 85 minus 54, and then 31, you realize that 31 is the same thing as 17 plus 14. That clearly tells you that the F will come in there. So you have 6s2, 4f, 14, 3, 5d, 10, 6p5. We'll write that out again. Let's get how do we arrive at that electronic configuration? Astatine will assume the xenon core. And when you're talking about the xenon core, you are talking of 54. And subtract 54 from 85. 85 minus 54. 5 minus 1, 4, 1. 31. What is 31? 17 plus 14. Therefore, it means that the F will come in between. And at that point, you have 6s2, 4f14, 5 d10, and 6p5. If you add up that, you arrive at 85. Now, there's something you shall have noticed here. You will notice that every member of the group shows that and shows that. What does that imply? It implies that if you draw the px, py, and pz orbital, you start the feeling as normal as you are. You realize that you have a single electron that is not paired. A single electron that is not paired. For this reason, we say that they show peculiar coloration. Peculiar coloration. They show coloration. And for you to say they show coloration, we need to explain how do they show up this coloration? How do they show this coloration? The fascinating coloration ratio arises from the ability of these to absorb. Remember, behind it are low-lying d orbitals. Low-lying d orbitals. So it has the ability of absorbing. And these d orbitals are vacant. When they absorb, they will display the complementary color after complementary color after having absorbed light at a certain wavelength from white light. Furthermore, as we do say in chemistry, when we talk chemistry, we must talk ability to react. When we talk chemistry, we must talk ability to react. So we'll look at the reactivity. We'll look at the reactivity of the halogens. Halogens are very reactive, and reactivity of halogens decreases as you descend the group. They are ordinarily, they are covalent in nature. But because of their high electronegativity, they are able to take or accept one electron to form an anion. Because they have very high electronegativity and high electron affinity, they are able to accept one electron to form a cation. Besides accepting electron to form a cation, they are also able to share their valence electron to form covalent bonds. In another, they are also able to form cation. They are also able to form cation in a very peculiar reaction that we shall see as we go. So the first we want to see is how do they form. They are able to overlap their valence electron. If we see this, and we see this, and see this. This is a peculiar valence orbital of a halogen. Because of the presence of this single electron, they are able to share with yet another willing electronegative atom, such as hydrogen. And when they share, you realize that the hydrogen atom here will assume a positive charge, while the halogen will assume a negative charge. Therefore, the bond so formed between the halogen and hydrogen will be a polar covalent bond. That is to say, the bond will assume a charge. And when that happens, we say that if Hx dissolves in water, it will yield an acid, where you will see the possibility of forming a hydroxonium ion in the medium due to the presence. That is the point that we would say that he may assume a positive charge. So at that point, we move ahead to see how do they form non-polar covalent bond. How do they form non-polar covalent bond? They will form non-polar covalent bond when they react with themselves. That is to say, if chlorine reacts with chlorine to form chlorine 2, we call it homonuclear molecule. Homonuclear, showing that there shall be no charge separation, there shall be no electronegativity disparity. Therefore, you have chlorine, chlorine. When you have chlorine, chlorine, there shall be no charge separation. And here it has a zero oxidation state. Furthermore, it is also able to react. It is also able to react with the electropositive species or atom. When it reacts with the electropositive species or atom, he will naturally assume a -1 state, because the electropositive atom, like in the case of sodium, for instance, sodium atom has 1 electron in the valence orbital. The 1 electron will be donated, and you agree with me, it has 7. 1, 2, 3, 4, 5, 6, 7. At this point, the sodium atom will acquire, or any other group 1 element. It must not be sodium alone. It must not be sodium alone. Potassium will react as such, rubidium will react as such. It will give away, this electron will be given away on the acquisition of ionization energy, and the resultant ions will take the form of sodium, no electron, the halide, at that point you see that the electron has moved from sodium to here, and that will become a -1 and a +1. By -1 and +1, something comes to mind. Something comes to mind that when polarity, then there is polarity disparity, there will be an electrostatic force of attraction. Electrostatic force of attraction will ensue. Therefore, an ionic bond shall be formed. Ionic bond shall be formed. Furthermore, we need to recall that the halogens are able to combine with themselves. That is to say, apart from us having chlorine, we are able to have bromine, chlorine, or iodine, chlorine, as the case may be. Where halogen react with a fellow halogen, the halogen below in the group shall assume a positive charge, while the halogen above shall assume a negative charge. The same thing applies here and here. But here, if it is in chlorine, if it is in chlorine, the charge will be 0, 0. There shall be no charge. So that is where we are. And we say that halogens exhibit variable oxidation state. Variable oxidation state. Variable oxidation state. That is to say, halogens are able to show -1, 0, +1, +2 is not possible. +2 is not possible with the halogens. Halogens do not show +2 oxidation state. They will show +3, +4, +5, +6, and +7. That is to say that it is possible for halogen to give away all the seven valence electrons. Agree, this is NS. As we have stated earlier, they show the generalized electronic configuration of NS2NP5. What we mean now is that it is possible for halogen to form a covalent bond or ionic bond, ionic, at +1, -1, +1, +3, down to plus, but cannot form at a +2 state. We had already discussed when it shows, when halogen can possibly show, a -1, when he reacts with a less electronegative, he will draw the electron to himself. If you have HX, for instance, he will draw the electron, the shared electron, more to himself. Therefore, he will assume a -1 oxidation state. If he combines in a homonuclear form, which is XX, without disparity in electronegativity, it will show oxidation state of 0. Furthermore, it is also possible for the halogens to combine if you have Cl2O, you remember that this is 8 and this is 17. And because it is 8 and 17, it is higher up, while 17 is down in the periodic table. If you check the periodic table, see that 17 is down. And because 17 is down, he will assume a positive status, while oxygen that is higher up will assume. And at this point, you have OCl, Cl, and the Cl here will become positive, and you have Cl2O. When we present our PDF format, the same applies with other except iodine. We also have a possibility of having HClO2. HCl2O2, oxygen will naturally take it -2 into 2 equals -4. And for these to attain a stable oxidation state for the molecule coming, which has to equal 0, you can say X plus y plus minus 4 equals 0. Here, you agree with me that he will take a plus 3, while hydrogen will take a plus 1. That is when this will equal 0. So here, x becomes plus 1 plus 3 plus into minus 4 equals 0. Meaning that here, for you to have this, if you want to calculate it, you can calculate it on your own. And calculate it on your own, you have x plus y plus into minus 4 equals 0. X here is plus 1 plus y minus 4 equals 0. Meaning y equals 4 minus 1 equals 3. Therefore, y equals plus 3. And that becomes the oxidation state of chlorine in this reaction. Chlorine. Furthermore, chlorine can further react with oxygen to form Cl2, ClO2 equals 0. Minus 2 into 2, x plus minus 2 into 2 equals 0. X minus 2 equals, x minus 4 equals 0. X equals 4. Therefore, in this compound, the halogen presents as a plus 4 species. A plus 4 species. It is also possible for us to have several other such situations. You have the plus 7, which we talked about when we react HClO4, HClO4. You agree with me? This is minus 8. You already know how to do that. Plus 1. So plus 1 plus x plus minus 8 equals 0. That one works out itself. So we have seen that they display variable oxidation state. And we now look at, in displaying variable oxidation state, we look at reactivity of the halogens. Reactivity of the halogens, starting from fluorine, chlorine, bromine, iodine, and we will just keep away this. You realize that this, because of its small size, has the highest electronegativity, but it has a very low bond breaking energy. The bond between fluorine and fluorine breaks easily because there is a perpetual repulsion between the two, because they are too close. The electrons are just too close due to the small size. Apart from that, when he breaks to form a 2F, the F here is very reactive. It has the ability of taking electron from anything. So much so that it can even react. It can react with gold. It can react with gold. It can react with xenon. Remember, xenon is a noble gas. Is supposed to be inert. It shouldn't react. But fluorine can. But as you come down, reactivity decreases. Reactivity decreases, electronegativity decreases with increase in atomic radii. There is increase in atomic radii. When the the radius increases, the valence electrons are further away from the effect of the nucleus. Therefore, they are weaker and can easily be ruptured. For this reason, iodine will assume a more electropositive property. Iodine will assume a more electropositive property than fluorine, than bromine, than chlorine. He will. Than chlorine. Our note will show you how that happens. Furthermore, in talking about reactivity, the halogens, even though their reactivity decreases down the group, has the ability of reacting with ion 2 in aqueous medium and oxidize it to ion 3. And you see this by the change in coloration from green, as the case may be greenish blue, light green, to reddish brown. To show that there is an oxidation. And for that, you see when you react X2, there will be, halogens will be able to oxidize. But when it comes to fluorine, the reaction is different. When it comes to fluorine, that reaction is slightly different. We also know that the halogens can react with phosphorus. Halogen can react with phosphorus 15. How do we make phosphorus 15? If we look at 1s2, 2s2, 2p6, 3s2, 3p3, gives you 15. So long as there is the existence of the 3 quantum states, the 4s2, the 4s will be 0, the 3d will be 0. The ability to accommodate the 3d, the 3d, which is low lying and vacant, will predispose phosphorus to octet expansion. And because phosphorus can undergo octet expansion, it is possible you have px3 and px5. Which of these 3 will form will depend on the electronegativity. Of the halogen. And we realize that here fluorine will be the best of pair here, PF5, while here will be mostly PCl3 or PBr3, as the case may be. Furthermore, it is also possible for the halogens to react with water. Reaction with water. They will react with water. You have X2 plus H2O. In the course of reacting with water, if the X here is fluorine, he will readily rupture water. Fluorine will readily rupture water to form HF and oxygen will be evolved. At that point, I think to go there, and 4 goes there. 4 goes there. That's a balanced equation. This is how fluorine will react. That is how fluorine will react. But the lower species, chlorine, will undergo disproportionate redox reaction. What that means is, when you say it undergoes a disproportionate redox reaction, which we call disproportionate redox reaction. What do we mean there? The very same, or you call it auto-ionization. Auto meaning self. Ionization. Auto-ionization. When halogen, like in the case of chlorine, undergoes auto-ionization, you have the X2 become X minus plus X. He will ionize itself. In that instance, let's take an instance where chlorine reacts with water. Chlorine reacts with water. If chlorine reacts with water, we have already seen fluorine. Cl2 plus H2O. As we have seen, there shall be auto-ionization. Auto-ionization. Agreed that HCl shall be formed. HCl. But hypochlorous will also be formed due to the auto-ionization. It will form hypochlorous. It is also possible for the halogens to react with the alkali metal group. As in their hydroxide format. Now, there shall be 2 conditions of reaction. Reaction number 1, in a cold stroke dilute medium, and in a hot stroke concentrated medium. Cold and dilute and concentrated medium. In a cold and dilute, you can have X2 plus 6 MOH, for instance. When that happens, MX will be formed conventionally. Sooner than MX is formed, MXO3 will also be formed. Then water will be formed. And you can balance the equation conventionally by putting that. And you realize that in dilute, this will happen this will be the product of this reaction in a dilute cold dilute cold reaction system. But if the environment changes, if the reaction environment changes to hot and concentrated, the very same reaction will take the form of 3x2 to react with 6MOH, where M here is an alkali metal, and the product of that reaction will be MX, can take the form of 5, MOX, as we had it here, MOX, MOX, and water, and water. This will be the situation. This will be the situation in a hot conc reaction condition, hot and concentrated reaction condition. When we are looking at the reaction of fluorine, I will still repeat this, fluorine is different. Fluorine is different. Fluorine is different. Fluorine is different. Fluorine in its characteristic manner. Fluorine in its characteristic manner. If you have 2F2 reacting with 2MOH, and these will first become 4F. It must first of all translate into 4F before it will react to give you 2MF. MF will be formed in the first instance, then there will be OF2. You will see that here in this reaction, even though oxygen lies side by side with fluorine, so long as it occurs to the left, in the periodic table to the left of fluorine, he will assume a positive charge, while fluorine will assume a negative charge. Not just because it lies to the left, also because fluorine is excessively electronegative. Furthermore, water will be formed. And this reaction occurs under any condition. The reaction condition must not be cold, must not be concentrated, must not be dilute. So far as it has to do with fluorine, the reaction will be spontaneously reacting to yield this. Furthermore, they can also react with ammonia. The halogens can as well react with ammonia to release nitrogen. But the most interesting reaction that we want to discuss now is the one we call charge transfer. Charge transfer is an exceptional reaction of the halogens. It is an exceptional reaction of the halogens. This reaction is a physical-chemical chemical interaction. A physical interaction that assumes a chemical dimension. What do we mean here? If iodine, let's use iodine, is made to dissolve in an electron-rich solvent, such as benzene, we will find out that there shall be color change. There shall be color change from the conventional color of iodine. This color change is said to be because the benzene that is rich in electron rich, shall donate electrons into the low lying orbital of the halogen. When it donates electron into the low lying orbital of the halogen, and the halogen accepts, you will experience a color change. This dissolution, ability to dissolve, is a physical phenomenon. But that when this dissolution takes place, there shall be change in color. You will observe that if this same iodine is dissolved in carbon tetrachloride, there shall be no observed color variation. So if halogen dissolves in electron-rich donating medium, such that there is a variation in coloration within the reaction, we refer to that interaction as a charge transfer reaction. And the proven evidence is it can also dissolve in a non-electron rich as carbon tet. And when that happens, there shall be no variation. At this point, we will rather refer you to our Google Drive page. At the end of this clip, please, you will see our PDF link. Please click on the link, and you'll be able to see the PDF format of this lecture. At this point, we will conclude this as we say, see you next time. Thank you.